Welcome to the PG and UG students for the NET question solution platform, and this platform is also helpful for the different type of the competitive examinations such as NET, JAM and GATE examinations. I am discussing regarding the NET question solution 2025. First question is that for the following equilibrium, the correct match of the carbonyl compound, that is the hydration reaction with the carbonyl. In the hydration reaction, the carbonyl group react with that of the to form the gem-diol intermediate, and this gem-diol intermediate produces the different type of the diol compound, and their substitution variation, such as if the R equal to methyl in case of the acetaldehyde, then this is the gem-diol of the acetaldehyde, and this is the chloral. After the hydration reaction, it produces the gem-diol of the chloral, and this is the trifluorohexyl substituted acetone, produces the gem-diol intermediate. And we know that the intramolecular hydrogen bonding stabilizes the gem-diol intermediate, and this intramolecular hydrogen bonding stabilization effect is more favorable when the fluoride is present. And in case of the chlorine substituent, the intramolecular hydrogen bonding is not so much strong as that of the trifluoro substituent. So the equilibrium constant for the gem-diol intermediate is highest in case of the trifluoro substituted acetone compared to that of the chloral intermediate. And hence the order for this gem-diol equilibrium, that is the gem-diol equilibrium constant, is highest for the trifluoroacetone substituted compound, that is the hexatrifluoroacetone. Hexatrifluoroacetone has highest equilibrium constant, that is 1.2 × 6 with the intramolecular hydrogen bonding, then the chloral, and then the acetaldehyde. Here no hydrogen bonding is present, so the gem-diol intermediate is unstable, and hence the equilibrium constant is less, that is the 1.0. Next is that of the NMR spectroscopy problem. Here the two type of molecules are present. One is the compound where the methylene group present at the adjacent to that of the chiral carbon. That is, this is the chiral carbon, and this is the methylene hydrogen atom. And these methylene hydrogen atoms has different orientation. That is, one side has the fluorine and another side has the bromine. But here no chiral center is present. That is, the both sides has the fluorine. So this methylene hydrogen atom has similar to that of the first order type of NMR. That is, it can be splitted as n+1 rule as a quadrate, and the Pascal, according to the Pascal triangle, the ratio will be 1:3:3:1. But in case of this substrate, in case of the X substrate, and this X substrate has the chiral center, so the AB type of quadrate, that is, this hydrogen is splitted by this hydrogen, and this right side hydrogen is splitted by the left side hydrogen. So this equilibrium, this splitting pattern is similar to that of the quadrate, but it is known as the AB type quadrate. So the option 3 is the correct. Next is that of the stereochemistry related problem. Here the two substrate is given here, and two substrate means here the ethyl group, if this substrate is converted to that of the chair conformation, then this ethyl group come to that of the upside, and this bromine group come to that of the upside, and this chlorine group come to that of the below side. And after if we rotate it, and 180-degree rotation followed by 120-degree rotation, we get the similar compound is the given substrate. So if we rotate it, then this, after the conversion of this is the chair conformation, and this compound after the rotation with that of the 180-degree, and after the rotation 120, this is the identical with that. That is, the two conformations are identical to each other. Next is this is the very famous problem for the UG level, and that is the formation of the pentaerythritol, and this problem is come different type of the examination, and this is the reaction of that of the alpha hydrogen containing aldehyde in presence of the OH minus. It produces the carbanion, and this carbanion is added to that of the carbonyl and produces the hydroxymethyl substituted aldehyde. And this hydroxymethyl substituted aldehyde conjugated the aldehyde addition produces the trihydroxymethyl substituted aldehyde, and this trihydroxymethyl substituted aldehyde has no alpha hydrogen atom. So after the intramolecular Canniger reaction, that is the hydride shift of the O minus to that of the another aldehyde to produces the tetrahydroxymethyl substituted methane derivative, and this is known as the pentaerythritol, and hence the reaction involves that is the aldol condension followed by the Canniger reaction. So the option 4 is the correct. Next is the amino acid related problems. In the amino acid, this is the examples of that of the Edman degradation. In this Edman degradation, we have seen that the amine group is actually decoded. Amine group is the cleave the peptide bonds, and here this is the example of the dipeptides, and this dipeptide has the N-terminus residue, and this N-terminus residue reacts with that of the phenyl thiocyanide, followed by that of the intramolecular addition of this phenyl thiocyanide to produces the hydrantoin derivatives, and this hydrantoin derivatives along with that of the alanine residue, and this alanine residue, so the option, that is the alanine residue present in the deuterionic form, so the option A along with that of the D is the correct option, and the option 1 is the correct. Next is the acetyl hydrolysis. We know that what is the acetyl hydrolysis? After acetyl hydrolysis, the carbonyl group is generated. Here the some cyclic acetals are given, and in this cyclic acetal, the most important factor is that the substrate 2. In case of the substrate 2, after the acetyl hydrolysis, we know that the acetyl hydrolysis takes place via SN1 mechanism, that is the carbocation formation, the rate determining step for the acetal formation. But here, after the carbocation formation, the carbocation present in the bridgehead position, this is very unstable in case of the bread fuel. So this carbocation is very much unstable. So the hydrolysis rate for this bicyclic system is very much less, and this is the lower rate of the hydrolysis rate. So the option 2 is the option where the 2 is the present in the lowest rate. But here the 1 and 2, if we can explain between that of the 1 and 2, in case of the 1, the hydrolysis become faster as the para-nitrocphenyl has the larger leaving aptitude. So after the protonation with that of the hydroxyethyl oxygen, it can be easily deported, it can easily removed, and to give that of the corresponding carbonyl compound. So the option 2 is the correct. Next is that the hydrogenation reactions. In the hydrogenation reaction, here the different two type of the alkynes are present. One is the electron deficient alkyne. We know that this electron deficient alkyne has the vacant d orbital with that of the silicon atom, and this vacant d orbital can resonate with that of the pi bond and reduces the electron density on this pi alkyne system, and this is the electron rich alkyne. And this electron, we know that the electron rich alkynes has better affinity for the Lindner catalyst, so it can absorb in the electron rich alkyne system and to give that of the hydrogenation product. And we know that after hydrogenation we get that of the cis alkene, so the cis alkene is the final product. And this is the pericyclic reaction. In presence of the n-butyl lithium, here the carbocation is produced, and this carbocation has the this is the pentadienyl anion system, and this dienyl anion system has the 5 molecular orbital, pi atomic molecular orbital, and according to their electronic occupation, the site is the HOMO, that is the highest occupied molecular orbital, and the molecular orbital has the 2 nodes, and this corresponds to the 2 options. So the option 2 is the correct. Next is that of the following reaction occur under, this is another pericyclic reaction where the 2 hydrogen present in the trans orientation in the cyclic form, and after the pericyclic reaction, the 2 hydrogen come in the inside. That is the orientation has been changed. That is the up and down orientation converted to the 2 inside hydrogen. So this must be the bond rotation ring opening. So thermal bond rotation ring opening takes place, and this can be represented by the FOMO diagram where the bond rotation after the orbital orientation of the anti-clockwise direction, the 2 hydrogen go to that of the inside and the 2 alkyl group go to that of the outside. And this is the reaction of the addition of the alkene systems and the trichloro substituted methane radicals can add methyl radicals can add it to that of the alkene, that is the styrene, and these radicals can be stabilized by the phenyl ring via the resonance effect. But this radical becomes unstabilized in case of the butadiene substituted system, that is the isoprene molecules. And in the isoprene molecule, after the radical addition, the two trichloride system can undergo steric interaction with the methyl group. So this radical addition becomes unfavorable, but this radical addition comparatively favorable in case of the propene system. So the option C is the correct, that is the BCA. This is the option B, B and A and C. That the option 2 is the correct, not 3. Next is that for the reaction of R-bromide, ethanol and sodium ethoxide in ethanol, the correct match of the for the R group reaction. That is, this is the SN2 type reaction, and we know that in the SN2 reaction, with increasing the branching, the rate of the reaction can be decreases. And this the relative rate with that of the for CH3CH2, this is the relative rate, that is the 1, and if the R equal to methyl, then the rate becomes enhanced, that is the branch decreases, so the rate is enhances, that is the rate becomes 17. But in case of the with increasing the branching, instead of the propyl, the rate becomes thoroughly decreases, and with increasing the branching, the rate will be diminishes, and the option 1 is the correct option. And this is the acidity-basicity problem, and this is the imidazole unit, this is the bench imidazole unit. And we know that with increasing the pK value, the basicity will be increases. So the either the basicity between compare the basicity between the imidazole and the bench imidazole. In case of the imidazole system, the basicity is higher, as after protonation, the aromaticity is retained. In case of the bench imidazole system, here no resonance is coming where the aromaticity is lost. But in case of the bench imidazole system, the negative charge after the delocalization of the conjugate acid, the aromaticity is lost in the some conjugating structures. So this is the unstable, and hence it has lower pK value. The pK value of the imidazole system is higher. So the 1 is greater than 2. In case of the pyrrole and indole system, in case of the pyrrole, the pK value is 23.05, but in case of the indole, this becomes reduces to 20.90. Here, after protonation of the pyrrole system, the aromaticity is completely lost. But here, after protonation, one benzene ring is retained in the ring system, so the aromaticity is slightly reduced. So this conjugate acid is comparatively most conjugate acid is comparatively, that is the option 4 has higher acidity. 4 has the higher acidity than that of the 3. Next is that bond decision energy. In case of the bond decision energy, here the different type of the bond decision energy. We know that if we move from that of the top to bottom, then top to bottom the bond energy decreases. So the bond energy decreases means the carbon hydrogen has greater bond energy compared to that of the silicon hydrogen compared to that of the tin hydrogen. So the carbon hydrogen bond energy is higher bond energy, and tin hydrogen bond energy is the lower bond energy. Now we go to that of the coenzymes involved in the base. This is the decarboxylation of the histidines in presence of the pyridoxal phosphate. This is the vitamin B6. And the vitamin B6 can undergo react with that of the aldehyde with that of the amino acid, produces the imine derivatives, and these imine derivatives undergo protonation followed by the decarboxylation. It gives the decarboxylation is facilitated due to that of the strong resonance with that of the pyridyl ring, and hence the pyridoxal phosphate is the coenzymes for this biosynthesis. And the lowest energy polymer of butadiene has an energy beta energy, and resonance energy, if we see that this resonance energy is coming from that of the butadiene system, and the butadiene system, the resonance energy can be classified according to the equation E psi j equal to alpha mi mj into beta, and this mj value can be calculated by 2 cos pi j pi plus n plus 1 Here, in case of the butadiene, the n equal to 4, that is the 4 pi atomic orbital is present. So 4 plus 1, and the lowest energy means this becomes 1. So the calculation becomes 1.618, and this is the 1.618 beta, alpha plus 1.61 beta. Similarly, from this equation, we can easily calculate the mg value for the different pi atomic orbital system, and get that of the alpha plus 1.618 beta for the lowest energy pi atomic orbital. And this is the pericyclic reaction of the 1,2-divinyl cyclopropene system, and this is the cis orientation form, and it goes to the boat conformation to give that of the cycloheptadiene system, and here the trans and cis isomer converted to that of the cycloheptadiene system via the boat conformation. The reaction goes through the 3,3 sigma topic, and this is the example of the Cope reagent, and this Cope reagent produces the cycloheptadiene system. And this is the asymmetric reduction, and binary derivative of the ruthenium complex, and the ruthenium complex can reacted with that of the hydrogen, produces the octahedral intermediate, and this octahedral intermediate is the chiral octahedral intermediate, and this chiral octahedral intermediate has specific hydride donor sites, and specifically different type of the binary system produces the different isomers. Suppose if we take that of the R binary with that of the R configuration, that is the ligand is the corresponding RR, and the product is the S1-phenyl ethanol. In case of the, to get the S1-phenyl ethanol, we must take that of the RR dithane ruthenium chloride substrate, and this can be followed by the following reaction, where the hydride ion is shifted from the one phase, that is the top phase, and the OH group come to that of the bottom phase, and we get that of the S1-phenyl ethanol. And this type of the complex can be used for the different type of the chemical reaction for the asymmetric version, that is the Allard reaction, Poisson-Khand reaction, Deligne-Smith reaction, Heath reaction, cycloaddition reaction, etc. This is the samarium ardent catalyzed cyclization reaction, where the cyclopropane intermediate can be braked to give that of the, and consequently added to that of the alkyne system, and the addition always take place to that of the less substituted end of the alkynes, and produces this intermediate, radical intermediate 3, and this radical intermediate undergoes condensation, and followed by the oxidation, we get that of the substituted the cyclopentene system, and hence the option 1 is the correct option for this reaction. Next is that of the oxidative Hague reaction. In this oxidative Hague reaction, we have seen that the OH group can add to that of the alkene and produces the oxidation complex, that is the OH group is added here to give that of the pyran intermediate, and this pyran intermediate can add to that of the alkene to give the palladium 2 intermediate, and this palladium 2 intermediate after the beta hydrogen elimination to get that desired product, and the palladium 0 is further oxidizes by the air to get that of the palladium 2, and this is the oxidative addition of the Hague type reaction. This is the example, interesting examples of the Barth reaction, and this is the exceptional case where the methoxy group can be eliminated from the substrate, where we know that the methoxy group can resonated with that of the carboxyl group by the resonance push-pull effect, and then after the push-pull effect, the methoxy group produces the methoxynium ion, and this methoxynium ion can add it to that of the electron and to get the ether derivative, and this ether derivative of the further elimination to get the to eliminate the methoxy group, and after the further branch reduction we get the desired product. So the option 1 is the correct option. And this is the one type of the pericyclic reaction, and then the carbonyl reprotection reaction. In this pericyclic reaction, the n-butyl lithium can in this conversion, the n-butyl lithium can deprotonated the adjacent to that proton to that of the sulfur and get that of the alkyl substituted derivative, and this alkyl substituted derivative undergoes 3,3 sigmatropic shift, that is the Cope type rearrangement, where the n-butyl present in the equatorial position, and after the heating and then the carbonyl formation get the desired product. Here the stereochemistry is the anti, and this is the anti-stereochemical product. And this is the conformation of this related problem, where the different types of triazine substituted cyclohexane derivative, where the nitrogen atom is substituted by the tertiary butyl group, and if the nitrogen atom present in the tertiary butyl all are present in the equatorial position, but the 3 lone pair has present in the axial orientation, there is strong electronic repulsion which can unstabilize this conformation. And here if the tertiary butyl group is the actual point, their strong steric interaction is present. So the conformation is that the two tertiary butyl group is in the equatorial position, and another tertiary butyl group is present in the axial position. This is the preferred conformation. So the option 2 is the correct. Now this is the nitrogen intermediate problems, where the nitrogen intermediate means that after the elimination of the nitrogen gas, it produces the nitrogen intermediate, and the hydride ion is shifted here and produces the amine derivative, and the cation is formed, and then this cation is attacked here to give the hydride substituted intermediates. This is the oxidation problem, where the tempo in presence of the NCS in DCM water produces the carbonyl group. Selectively, the less inert alcohol is oxidized, but the more inert alcohol, that is the 2-degree alcohol, is not oxidized here. Here, the oxidation mechanism is that the tempo is oxidized in presence of the NCS, produces intermediate, and this intermediate is helped to get the alcohol to oxidized product, that is the aldehyde, and it further hydride shifting to get the tempo as the catalyst, that is the tempo, recycling the tempo, that is the tempo used as the catalyst for the oxidation of the alcohol to aldehyde. If in the option 4, the sodium hypochlorite and sodium chloride is used, then the aldehyde is further oxidized to carboxylic acid. So the option 4 is not the correct. Here this is the Oppenheimer oxidation and the MPP reduction, and in this case the MPP reduction will be take place. Here the ester group is coordinated with that of the aluminum isoperoxide, and the hydride groups come from that of the back side, and hence the OH group comes to the top side, and after the OH group formation, it can undergo easily electronization to give the electron intermediate, and this electron intermediate present in the upside, and hence the aluminum is coordinated in the downside, and the hydride is transferred from that of the back side, and you get that of the cis hydroxide product. So the option 3 is the correct. This is the substitution product, where substitution reaction, where the alcohol, this is the one type of the Mursino-Goodine reaction, where the triphenyl phosphine oxide is eliminated in presence of the tri-in-butyl phosphine. The tri-in-butyl phosphine react with that of the selenium to give that of the positive intermediate, and then the hydroxy group is attacked here and to give the selenium anion intermediate, and this selenium anion intermediate attack to that of the SN2 type mechanism to give the triphenyl phosphine oxide. Here the SN2 dot type attack is not favorable according to the least portion principle, where the bond order change is minimum, so here the addition is not take place, that is the SN2 direct, SN2 addition will occur. And this is the hydroboration reaction problem, where in the hydroboration, this is sterically hindered hydroboron compound, and this hydroboron compound can add to that of the 6-ethyl boron and the less substituted end, and we get the alcohol substituted product after the presence of the NOH and H2O. And this is the elimination related problem, where the elimination, beta hydrogen elimination will occur, and this is the stereochemistry of where the hydrogen atom present in the opposite side. This is the trio conformation, and in this trio conformation, if we convert it to movement projection, the two enemy group can be eliminated, and we get the desired given product, that is the 1,2-diphenyl 1-propene, and this can be obtained from that of the from this compound. So the option 3 is the correct. And this is the substitution reaction, where in the substitution reaction the 1,2 elimination followed by 1,4 elimination take place. Here the 1,4 elimination take place, that is the NGP type reaction, and then 1,2 addition we get the reaction product. And this is the protein reaction, where the C-terminus group can be eliminated, but that is the allylic type intermediate, and this allylic type intermediate can add with that of the palladium and easily help to clip the alkoxy bond to give that of the alkene, and we get the specifically the morpholine and palladium PPH 344 is used for this deprotection reaction. This is the NMR related problem, where the different type of the proton is present in the alkene system, where the geminal coupling, vicinal coupling is present, and here the HA can couple with that of the HB or HC, but HA can couple with HC via trans orientation, so that coupling constant is higher, and trans coupling constant is 13 Hz, but the cis coupling constant equal to 7 Hz. But HB can couple with HC via the geminal coupling as a doublet of doublet equal to 2 Hz, and this can also couple with that of the cis coupling. This is equal to 7 Hz. So the option A is the one is the correct option. Next is the Hammett equation problem. In the Hammett equation, we know that the rho value can be changes if the rho is if the electron withdrawing group, that is the positive charge, is present on the transition state after the reaction, during the reaction. This is the Friedel-Crafts reaction. Friedel-Crafts reaction, we know that the aluminum chloride can coordinate with that of methyl chloride, produces the methyl cation, and this methyl cation added to that of the methyl group and produces the positive charge on the benzene carbon. So the positive charge creation on the benzene nucleus indicated the rho value is negative. That is the charge is positive. If the charge is positive, that is the electron deficient is nature on the transition state, the rho must be negative. Rho must be negative. Hence, in the Friedel-Crafts reaction, rho must be negative. But here, in this case, the reaction will occur in the two states. Here, after the protonation on the carbonyl group, the charge is positive on the transition state, so the rho is negative. And if the cyanide is attacked here, the rho is positive. So the positive and negative can be neutralized, and hence it becomes somewhat positive, and so the reaction option 1 is the correct option. And this is the major product in the following reaction, means this option, this is the three option is the correct, and this can be represented very nicely, where the our sir Dr. Satyajit Ray actually giving this problem clearly to give this answer, where this is the Newman projection can be represented here, this conformation, and this after the Newman projection, this is the fragmentation type reaction, and this red bond can anti-periplanar with each other, and after the elimination of this group and produces the fragmentation, after the fragmentation reaction gives the alkene product, and this hydrogen comes to that of the antiposition, so the option 3 is the correct option. And this is the another type problem, where Lewis acid promotes cyclization reaction, where the cascade reaction will take place in presence of the phenoxy substituted derivatives, where the oxygen is lone pair is added here, and then this alkene is added here, and to give the epoxide cleavage and to give the desired product. Here, this if you see that orientation, and if you see the orientation, this methyl group and this methyl group go to the top, the left side. So these two methyl must go to the top side, and this hydrogen atom, where the hydrogen atom and the methyl group the opposite side. So this hydrogen atom must go to the bottom side. So the stereochemistry can be represented in that way. That is the two methyl group in the left side. So this two methyl group the upside. This is the 19F NMR. Where 19F NMR, we know that 19F NMR of the ClF3 molecule. This is the TBP structure, T-type structure, or the axial and equatorial fluoride is present, and these two axial fluoride is one type and equatorial fluoride another type. This axial fluoride is treated by the equatorial fluoride as a doublet, and this fluoride, equatorial fluoride is treated by the two axial fluoride as a triplet. So the option C is the correct option. Again, in case of the ClF5, all the here the two fluoride, and one is the axial fluoride, another is the four fluoride is present in the equatorial position. So the first option is the doublet and triplet, and second option is the doublet of Weinberg. That is the 4 plus 1 equals to 5, and 1 plus 1 equal to doublet. And the last problem of this organic chemistry of this year, this is the isophenolic and halogenation of the isophenolic. In case of the halogenation take place, the nitrogen lone pair is attacked here, and to produce the Br minus is attacked here, and after the Br minus, it produces the intermediate after the halogenation, after the elimination followed by the halogenation. Actually, here the Cl minus will attack, not Br2. In presence of the HCl, the Cl minus is attacked here, so the Cl is come here, and after the conjugation with the nitrogen lone pair with the bromine, we get the product, which after the elimination of the HCl, we get the product. Thank you for the watching of the video. Some mistake is also present. This will be clarified in the next